Hello, so I am Jackson from Arc Robotics, and this video will be discussing PIDF, or just PID because most of the time you won't see F added unless there's some sort of force or value that is going against or with some control that you're trying to work with. PID is used to control some action that requires some sort of error, right? So that means that you need some sort of measured value that you have, right? Say, for instance, the current position of a ball. And then we have some set point, meaning the place that we want the ball to be. So say we have a ball, and we have a sensor here. And the sensor measures the distance between itself and the ball. As the ball gets closer, we expect the difference between the measured value and the set point, because let's say we have the set point here, right? So as it gets closer to that set point, we expect the error, the difference between those 2 points, to decrease. And as it gets further away, we expect it to increase. So we'll define our error function, the error given time, as our set point minus our measured value given that time. Let's say that our ball is currently three meters away from a sensor. Yes, it's a good sensor. And let's say that we want it to be only 0.5 meters away. Right? So our set point is 0.5 and our measured value is 3. So we would expect it to start moving this way and start slowing down as it gets closer and closer and closer to this point. Now, this is relative to distance, and this is where our p value comes in. So let's move this equation up top, and we'll change the color. Actually, we'll leave it as blue for p. So we're going to have E of t equal our set point minus our measured value given time. So m of t. All right. We have this as our event. This is what we want to control. Let's control the distance. So as it gets closer and closer, we want it to slow down, which means that we're setting our current control value, right? Our control value, which we'll say represents the how the motion of this ball as it gets closer or further away from the sensor. Okay? We'll refer to this as mu of t. This is our control function. Mu of t will be our control function. The next thing we're going to want to do is we're going to take a look at our error. Well, our current error is 3 minus 0.5. So let's say that our time right now is 0. So our error right now is 2.5 meters. Let's say that at 1 time value, let's say 1 second, it's currently 1.0 meters away. That's our error, right? And let's say E of 2, we're at half, and then E of 3, we're this far, and then let's say at E of 4, that's when it reaches 0. Alright, so we have 1 second intervals between there and there. So what we're going to do for our control value is we're going to take some constant, we'll call that Kp. So that is how you would model that. And then you would have some arbitrary Kp value that you've tuned or changed in order to meet this situation. So again, as we get closer and closer to this point right here, our distance is decreasing, and so this is relative to our position. So when you're dealing with position, say a lift on your robot, right? Well, when you have a lift on the robot, you can get away with just P control, meaning that if you're just going up to a position, you don't care about anything else other than just the position of the lift, you can do fine with just P control, which means that you're just using this for your control function. You can get away with that because all you care about is the final distance and the initial distance, and the distance as it gets closer. You don't care about, oh, is it going to overshoot, which would require D, or, oh, is it going to be a little bit off from, or is the air going to be a little bit too large for our liking, which would require an I, and then, oh, is it going to be a little too small because of gravity, which would require F. Lifts are a good example of PIDF, but you can get away with just using P control for them on your robot. So that is our P. Next one we're going to talk about is our derivative, D term, right? Derivative is going to be a little bit easier than our integral term. Feed forward is just adding a value to the end, so we can actually just do that right now. Feed forward means that you're accounting for some gravity value, so we just add a constant to the end that we tune. Adding KF. Alright, let's go back to this. This does not rely on the error at all, because we're just accounting for some constant. Then we have this. So our set point again is at 0.5, but say we want it to stop here, right? So right now we want it to be at 0 meters per second at this point, which is 0.5 meters away, right? And right now it's 3 meters away, and it's traveling at a speed of 1 meter per second. Okay. Now this is not accurate to a good representation, but this is just an example, right? So say we're traveling at 1 meter per second and we want it to be 0, right? So we want it to be at 0, just in general, and then let's not worry about that distance, right? But we just want it to be at 0. So the error, right? Our error function here has nothing to do with the position. So if E of t is our position, then what represents our velocity? The derivative of the position, which would be E prime of t. So how do we get E prime of t? Well, E prime of t, since this is position, right? If you think about it, slope is just a measure of change over time, right? Just the rate of change. Now, since our x value, right, in this case, instead of x we have t, we would instead use t as our base. So we'll use delta t, right? Now, for this, we have to have some arbitrary period. We'll call this dt, all right? Some arbitrary period. Let's add this to our reference things up there. So dt, something we need, right? So we have some arbitrary difference in time. So we want to take our final error and subtract that from our initial error and then divide that by our arbitrary change in time. So we're going to add kd, which is just our derivative constant, which again is tuned, times, and this is going to be times that final error, which is going to just be E of t plus dt, right? But let's just say E of t in this case, because we want t, because currently t is our current value, and then we're going to subtract our previous value, which was t minus dt, and then we're going to divide that by dt. So this is our previous error, and this is our current error. We're going to divide that all by dt and multiply that by kd. All right, that's it. That is our derivative term. And the next one, or the last one really, is I, which is just to account for a bit more error. So we want to account for the total error that has accumulated over time. So how do we do this? Well, we just add some constant value times the total error that has occurred. Let's refer to that as times sigma E of t. Okay? And then from t equals 0 to some number n. And that's it. That is our PIDF control. And so this is how you would control something that requires a set point and has a measured value, and we want to reach that set point. You can also declare a tolerance, say you want it to get arbitrarily close to that value, you want it to approach that value, but it doesn't necessarily have to reach that value. And so that is how PIDF works.